Here's something that'll bother you. I guarantee it. Last year, I had a student come to me and say, Professor Feynman, I missed my bus this morning by about 12 seconds. If I had just tied my shoes a little faster, I would have caught it. And because I missed that bus, I missed my first class, which meant I missed the quiz, which meant I had to take the makeup exam, which was harder, which dropped my grade, which changed which graduate school I got into. And he looks at me with this pained expression and says, did tying my shoes slowly ruin my life? Now most people would say, oh, don't be silly. That's just bad luck. One little thing can't change everything. But here's what's going to bother you. Mathematically, he might be right. And by the end of our time together today, you're going to understand exactly why. You're going to see that when it comes to chains of events, when things happen one after another and each thing depends on the thing before it, the mathematics tells us something deeply unsettling. Small things don't just add up. They multiply. And when you multiply, well, that's when things get wild. Let me start with something simple. Something so simple you might think I'm wasting your time. But stay with me. Suppose I have a coin, a fair coin. I flip it once. What's the probability I get heads? 1/2. Fine. Now I flip it again. What's the probability I get heads twice in a row? Well, it's 1/2 times 1/2. That's 1/4. Still simple. Now here's where it gets interesting. Let me flip it 10 times. What's the probability I get heads all 10 times? It's 1/2 multiplied by itself 10 times. That's 1/2 to the 10th power. That's about 1 in 1,000. We went from 1 in 2 to 1 in 1,000 just by doing the same thing 10 times. But wait, let me flip it 20 times. Now the probability of all heads is about 1 in 1,000,000. 30 times, 1 in 1,000,000,000. See what happened? Every time I added 10 more flips, I wasn't adding a little bit of improbability. I was multiplying by 1,000. This is the first thing you must understand about probability chains. When events are linked together, when each one has to happen for the whole sequence to happen, you don't add the difficulties. You multiply them. And multiplication is a vicious operation. It doesn't play nice. Let me give you a more practical example. Suppose you're trying to land an airplane. This is a real engineering problem. You have to get the approach angle right. You have to get the speed right. You have to deploy the landing gear. You have to adjust for crosswind. You have to flare at the right moment. You have to touch down on the correct part of the runway. Let's say there are 10 critical steps, and each one you do correctly 99% of the time. 99%! That's pretty good, right? That's an A+. What's the probability you do all 10 correctly? It's not 90%. It's not even close. It's 0.99 to the 10th power. That's about 90%. You just lost 9% of your reliability, even though every single step was 99% reliable. Now suppose there are 100 critical steps. 0.99 to the 100th power is about 37%. You've got a 63% chance of something going wrong somewhere in the chain, even though every individual step is almost perfect. This is why engineers are so obsessed with redundancy. They understand the tyranny of multiplication. Let me give you another way to see this. Think about a factory assembly line. Suppose you're making a radio. There are 50 components that have to work. Each component is 98% reliable. 98%! That sounds fantastic. But multiply 0.98 by itself 50 times, you get about 36%. More than half your radios don't work. This is why quality control became such a big deal in manufacturing. Every fraction of a percent improvement in individual component reliability translates into huge improvements in the final product. If you can get each component to 99%, your radio reliability jumps to about 60%. At 99.5%, you're up to 78%. At 99.9%, 95% of your radios work. You see the leverage? Small improvements in individual reliability create large improvements in chain reliability. But it works both ways. Small degradations cascade into catastrophe. This is also why I tell my students to check their work. Suppose you're doing a long calculation with 20 steps, and at each step there's a 5% chance you make an arithmetic error. The probability you get through all 20 steps without an error is 0.95 to the 20th power. That's about 36%. More likely than not, your answer is wrong somewhere. The solution isn't to be more careful at each step, though that helps. The solution is to break the chain, check intermediate results, use estimation to catch gross errors. Do the problem a different way and see if you get the same answer. Each check is an opportunity to catch and correct an error before it propagates. But here's what's even more interesting. So far, I've been talking about independent events. Each coin flip doesn't care about the previous one. The coin has no memory. But what happens when the events in our chain are not independent? What happens when what occurred before actually changes what can occur next? This is where things get really juicy. Let me tell you about a game. Imagine you have a bag with 10 marbles. 7 are red and 3 are blue. You reach in, eyes closed, and pull out a marble. What's the probability you get red? 7 out of 10. 70%. Simple. Now, here's the twist. You don't put the marble back. You reach in again. What's the probability you get red the second time? Well, it depends. If your first marble was red, now there are only 6 red marbles left out of 9 total. So the probability is 6 out of 9, about 67%. But if your first marble was blue, there are still 7 red marbles, but only 9 total. So the probability is 7 out of 9, about 78%. You see what happened? The first event changed the probability of the second event. This is what mathematicians call conditional probability. The probability of the second thing happening given that you already know what happened with the first thing. Now let me ask you a more complicated question. What's the probability that you pull out 2 red marbles in a row? You might think, well, it's 70% times 70%, so 49%. But that's wrong. That would be true if you put the marble back each time, but you don't. So the correct calculation is this. The probability of getting red first is 7 out of 10. Given that you got red first, the probability of getting red second is 6 out of 9. So the probability of both is 7 over 10 times 6 over 9. That's 42 over 90, which is about 47%. It's a small difference, but it's a real difference. And this difference gets bigger and bigger as you extend the chain. Now, here's something subtle that most people miss. The order matters. Let me show you why. Suppose I change the question. What's the probability of getting 1 red and 1 blue in any order? Now, there are 2 ways this can happen. Red first, then blue, or blue first, then red. Probability of red first, then blue, 7 over 10 times 3 over 9 equals 21 over 90. Probability of blue first, then red, 3 over 10 times 7 over 9 equals 21 over 90. Same number. The order of events doesn't change the probability when we're looking at the same combination. This is because multiplication is commutative. 7 times 3 equals 3 times 7. But the individual steps do depend on order. 7 over 10 is not the same as 7 over 9. The numbers work out the same only because both orders lead to the same final state. This might seem like mathematical trivia, but it's actually profound. When we ask what's the probability of ending up in this state, we often have to sum over all the different paths that could get us there. Some chains of events are more likely than others, but they might all lead to the same place. This is actually how quantum mechanics works at a deep level. A particle going from here to there can take many different paths, and we have to add up the contributions from all of them. But that's a topic for another day. Let me extend this chain. What if I asked you to pull out 5 marbles, one at a time, without replacement, and I want them all to be red? Now the calculation gets interesting. First draw, the probability of red is 7 over 10. Second draw, if the first was red, probability is 6 over 9. Third draw, if the first 2 were red, probability is 5 over 8. Fourth draw, if the first 3 were red, probability is 4 over 7. Fifth draw, if the first 4 were red, probability is 3 over 6. Multiply them all together. 7 times 6 times 5 times 4 times 3 divided by 10 times 9 times 8 times 7 times 6. That comes out to about 8%. Not bad, But we started with individual probabilities of 70%, 67%, 63%, 57%, and 50%. Each one seems fairly likely on its own. But the chain? The chain is unlikely. This is the mathematical structure behind that student's complaint about his shoelaces. It's not just that one thing happened. It's that one thing happened, which affected what could happen next, which affected what could happen after that, and so on. Each link in the chain isn't independent. Each link is shaped by all the links that came before. Now, I want to show you another way to think about this, and it involves a game I find absolutely fascinating. It's called the random walk. Imagine a man standing on a straight road. He's a little drunk. Every second, he takes one step. But here's the thing. He's so confused that each step is random. He might step forward or he might step backward with equal probability, 50-50 each time. After one step, where is he? Either one step forward or one step backward. After two steps, he could be two steps forward, two steps backward, or back where he started. You can work out the probabilities if you like. They follow a nice pattern. But here's the interesting question. After many, many steps, how far from his starting point do you expect him to be? His average position is 0, because forward and backward are equally likely. So on average, he's right where he started. But that's misleading. He's almost certainly not at 0. He's wandered somewhere. The question is, how far? The mathematics tells us something beautiful. On average, the distance from the starting point grows with the square root of the number of steps. So after 100 steps, he's about 10 steps away from where he started. After 10,000 steps, about 100 steps away. After 1,000,000 steps, about 1,000 steps away. Wait, let me say that again because it's so important. The drunk takes 1,000,000 steps, and on average, he's only 1,000 steps from home. That seems wrong, doesn't it? Shouldn't he have wandered much farther? But no. Because he keeps doubling back, canceling out his progress, the net effect grows much slower than you'd think. Let me make this even more concrete. Suppose each step takes 1 second. After 1 hour, that's 3,600 steps. The square root of 3,600 is 60. So after an hour of random walking, our drunk friend is about 60 steps from home. Not 3,600 steps. Just 60. After a whole day of walking, that's 86,400 steps. Square root is about 294. After walking randomly for an entire day, he's less than 300 steps from where he started. This is why diffusion is so slow. When you spray perfume in one corner of a room, the molecules are doing random walks, bouncing off air molecules, going left, right, up, down, forward, back. Each bounce is random. And because it's a random walk, the spreading happens with a square root of time, not with time itself. It takes 4 times as long to spread twice as far. Think about that. 4 times the time for twice the distance. If it takes 1 minute to smell the perfume from 1 meter away, it takes 4 minutes to smell it from 2 meters away. 9 minutes from 3 meters. 16 minutes from 4 meters. The relationship is quadratic in distance, or equivalently, square root in time. This is the opposite of what we saw with the coin flips. With the coins, the improbability grew exponentially. With the random walk, the distance grows only like a square root. Why the difference? The difference is that with the coin flips, we were asking for something very specific. All heads. Any deviation ruins everything. But with the random walk, the steps can partially cancel each other. 1 step forward and 1 step backward brings you back to 0. The mathematics is completely different. And this brings me to one of the deepest ideas in all of physics. When we have chains of events, the outcome depends critically on how those events combine. Do they have to all go one way, like the coin flips? Or can they add and subtract from each other, like the random walk? The mathematics is completely different in each case. Let me give you a physical example that I think about a lot. Gas molecules in a box. They're bouncing around constantly, hitting each other, hitting the walls. Each collision changes a molecule's direction and speed. It's like a random walk in 3 dimensions, with billions of steps every second. Now suppose I have a small particle of pollen floating in that gas. Robert Brown first observed this through a microscope, and it puzzled people for decades. The pollen jiggles around randomly. Einstein finally explained it in one of his great papers. The pollen is being kicked by the gas molecules. Sometimes it gets kicked left, sometimes right, sometimes up, sometimes down. Each kick is random, and the pollen does a random walk, just like our drunk friend. This is called Brownian motion. And here's the remarkable thing. By watching how far the pollen drifts over time, Einstein could calculate the size of atoms, because the size of the kicks depends on the size of the molecules doing the kicking. The random walk connects the visible world to the invisible atomic world. Einstein's calculation went something like this. If we know the temperature, which tells us how energetic the molecules are, and we know the viscosity of the liquid, which tells us how hard it is for things to move, and we observe how far the pollen drifts in a given time, we can work backward to figure out how hard the molecules must be kicking. And if we know how hard they're kicking, we can figure out how massive they are. And if we know their mass, we can figure out how many of them there are in a given amount of material. This was actually one of the most important pieces of evidence that atoms really exist. Before this, some serious scientists still doubted whether atoms were real things or just convenient fictions for doing chemistry. Einstein's random walk analysis showed that atoms had to be real, because only real atoms could explain the observed random motion of visible particles. So you see, this abstract mathematics about probability chains and random walks isn't just games, it's how we discovered fundamental truths about nature. Now, I want to address something that bothers a lot of people. I call it the great confusion about probability. People think that if something unlikely keeps not happening, it becomes more likely. This is completely wrong, and it has ruined more gamblers than I can count. Suppose I flip a coin and get heads 10 times in a row. 1 in 1,000 chance, roughly. Now I'm about to flip it again. What's the probability of heads? 1/2. Exactly 1/2. The coin doesn't remember. The coin doesn't think, oh dear, I've been heads too many times, I better be tails now to balance things out. That's not how physics works. Each flip is independent of every other flip. But wait, you say. Doesn't the law of large numbers say that things should balance out? Yes, it does. But it says they balance out by dilution, not by compensation. Let me explain this carefully because it's so important. Suppose you flip a coin 1,000 times and you get 600 heads and 400 tails. That's an excess of 200 heads, way more than expected. Now you flip it another 1,000 times, and you get roughly 500 heads and 500 tails, as expected. Now you have 1,100 heads and 900 tails. Still an excess of 200 heads. The law of large numbers didn't erase the excess, but the percentage changed. You started at 60% heads, now you're at 55%. If you flip another 8,000 times, getting roughly 4,000 heads and 4,000 tails, you'll have about 51% heads. The absolute excess stays the same. The percentage shrinks because the total grows. That's how probability balances out. Not by magical compensation, but by swamping the anomalies in an ocean of new data. People in casinos don't understand this. They see a roulette wheel land on black 5 times in a row, and they think, red is due. No, red is not due. Red doesn't even know what happened last time. Each spin is fresh. The only way the law of large numbers helps the gambler is if he plays forever. And the house edge guarantees that playing forever means losing everything. Let me give you a vivid example of why the gambler's fallacy is so wrong. Suppose you flip a fair coin and get heads 10 times in a row. This is unlikely, about 1 in 1,000, but it happens. People say, the next flip must be tails. Look at all those heads. It has to balance out. But think about it from the coin's perspective. The coin doesn't know it's been heads 10 times. The coin has no memory. If I showed you just the 11th flip in isolation, you'd say the probability of heads is 1/2. Nothing about the previous 10 flips changed the physics of the coin or the fairness of the flip. What's true is that the probability of getting 11 heads in a row is about 1 in 2,000. But that's a statement about all 11 flips together. not about the 11th flip alone. We can't go back and change the first 10 flips. They already happened. All we can influence is the 11th flip, and its probability is 1/2. Here's another way to think about it. There are 10,000 people, and they all start flipping coins. After 10 flips, about 10 of them have gotten all heads. Those 10 people might think they're on a special heads streak, but they're not special. They're just the ones who by chance got lucky. The 11th flip for each of them is still 50-50. The gambler's fallacy confuses the probability of a sequence with the probability of the next element in the sequence. They're completely different things, and this confusion has cost people their life savings. Now, let's get back to chains of events. I've been building up to something important. When we have events in a chain, and each event depends on what happened before, we get something mathematicians call a Markov chain. The name comes from a Russian fellow, Andrei Markov, who figured out the mathematics about 80 years ago. The key property of a Markov chain is this: the future depends only on the present, not on the whole history of how you got to the present. The system has no long-term memory. It just knows where it is right now. Let me give you an example. Suppose you're tracking the weather, but in a very simplified way. Each day is either sunny or rainy, and suppose the weather tomorrow depends only on the weather today, not on what happened last week. If today is sunny, there's an 80% chance tomorrow is sunny and a 20% chance it's rainy. If today is rainy, there's a 60% chance tomorrow is rainy and a 40% chance it's sunny. This is a Markov chain. The weather has only two states, sunny and rainy, and the transition probabilities depend only on the current state. Now here's the fascinating thing. Even though each day seems kind of random, the long-term behavior of the system is completely determined by those transition probabilities. You can calculate, for example, that in the long run, about 2/3 of days will be sunny and 1/3 will be rainy. The system settles into what's called a stationary distribution. But here's what's really interesting. If you start on a sunny day, the probability of being sunny on day 2 is 80%. On day 3, you have to account for both possibilities on day 2. If day 2 is sunny, there's an 80% chance day 3 is sunny. If day 2 is rainy, there's a 40% chance day 3 is sunny. So the probability of day 3 being sunny is 0.8 times 0.8 plus 0.2 times 0.4. That's 0.64 plus 0.08, which equals 0.72. 72%. See how it works? Each day, the probabilities mix. Sunny days can lead to rainy days, which can lead back to sunny days. The system explores all its possibilities, and the long-term behavior settles down to something predictable, even though the short-term behavior is random. This is actually how a lot of the world works. Stock prices, if you squint at them in the right way, look a bit like Markov chains. Traffic flow, the queue at the grocery store, even the way my students arrive to class late. All of these can be modeled, at least approximately, as chains of probabilistic events where each step depends on the step before. But now I want to tell you about something even more interesting. What happens when the probabilities in your chain aren't fixed, but can be affected by tiny, tiny changes in initial conditions? This brings us to the butterfly. Not the insect, though it is named after one. I'm talking about what some people call the butterfly effect. The idea is this. Suppose you have a system where each step depends sensitively on the previous step. Not just depends on it, but depends very sensitively. A tiny difference in how one step goes can lead to a huge difference in how the next step goes. And that difference can cascade. The classic example is the weather. Not our simplified Markov chain weather, but real weather. The atmosphere is governed by physics. It obeys laws. But the equations are so complicated and the system is so sensitive that a tiny change today can lead to a completely different weather pattern in 2 weeks. A meteorologist named Lorenz discovered this when he was running computer simulations of weather in the early 1960s. He ran a simulation, stopped it partway through, and then restarted it. but he rounded off one of his numbers. Instead of starting with 0.506127, he started with 0.506, a difference of 100,000th. The result? A completely different weather pattern emerged. The tiny round-off error had propagated through the chain of calculations and grown into something huge. This is different from what we've been talking about. The coin flip was independent. The random walk was random. The Markov chain had fixed probabilities. But Lorentz's weather model was deterministic. No randomness at all. Yet it was unpredictable, because tiny differences in starting conditions exploded into huge differences in outcomes. The butterfly metaphor comes from the idea that a butterfly flapping its wings in Brazil might change the air currents just enough to eventually cause a tornado in Texas. Now, don't take that too literally. A butterfly can't really cause a tornado, but the metaphor captures something true. In certain kinds of systems, small changes don't stay small, they grow. Let me make this more quantitative. In a chaotic system, nearby initial conditions diverge exponentially. What does that mean? It means if you have two starting points that differ by some tiny amount, say 1/1,000th, then after a certain time they differ by 100,000th. After twice that time, they differ by 1/10,000th. After 3 times, 1,000th. The difference keeps multiplying by the same factor each time interval. This is actually very similar to our coin flipping analysis, where improbability grew exponentially with the number of flips. The same mathematical structure appears, even though the physical situations are completely different. In Lorentz's weather model, the divergence factor was such that differences doubled roughly every 4 days. So a difference of 1 part in 1,000 today becomes a difference of 1 part in 500 in 4 days, 1 part in 250 in 8 days, and so on. Within a few weeks, the tiny initial difference has grown to dominate the entire forecast. The two weather patterns have diverged completely. This is why weather forecasting beyond about 2 weeks is fundamentally impossible, no matter how good our computers or measurements get. It's not a technology problem. It's a mathematical limit. The atmosphere is chaotic, and chaos wins. But here's something that surprised a lot of people. Not all systems are chaotic. Some systems are stable. Small perturbations stay small or even shrink back to zero. A pendulum swinging with a small amplitude is like this. If you nudge it slightly, it doesn't go crazy. It just swings at a slightly different phase and eventually returns to its regular rhythm. So, how do you tell if a system is chaotic or stable? This is a whole field of mathematics now. You look for something called the Lyapunov exponent. If it's positive, differences grow. If it's negative, differences shrink. If it's 0, differences stay roughly constant. The weather has a positive Lyapunov exponent. The pendulum has a negative one, at least for small swings. Now, here's what I want you to understand. This sensitivity to initial conditions is not the same as randomness. Lorentz's weather model was perfectly deterministic. If you knew the initial conditions exactly, you could predict the outcome exactly. The problem is that you can never know the initial conditions exactly. There's always some uncertainty, some round-off, some measurement error. And in a chaotic system, that uncertainty grows exponentially. Let me connect this back to our probability chains. When we have a chain of events, there are really 2 sources of unpredictability. One is genuine randomness, where even if we knew everything, we couldn't predict the outcome because nature itself is random. Quantum mechanics gives us that kind of randomness. The other is practical unpredictability, where the system is deterministic in principle but chaotic in practice. Weather gives us that kind of unpredictability. In both cases, the mathematics of chains applies. The probabilities multiply through the chain, small effects can accumulate into large ones, but the mechanisms are completely different. Now, let me give you a thought experiment. I want you to really think about this one. Imagine you're playing a game. You start with $100. Each round, you bet $1. If you win, you get your dollar back plus another $1. If you lose your dollar. The probability of winning each round is 49%. Just slightly less than 50-50. How long can you play before you go broke? Most people, when they think about this, Imagine it'll take a long time. After all, each round you have almost a 50-50 chance. Some rounds you win, some you lose. It should sort of balance out, right? Let's do the calculation. On average, each round you expect to lose, how much? You win with probability 0.49, gaining $1. You lose with probability 0.51, losing $1. Expected value is 0.49 minus 0.51, which is negative 0.02, 2 cents lost per round, on average. Over 100 rounds, you expect to lose $2. Over 1,000 rounds, $20. Over 5,000 rounds, $100. So, on average, you'll go broke in about 5,000 rounds. But wait, it's worse than that. Because of fluctuations, you might go broke sooner. The random walk nature of your bankroll means you'll sometimes be up, sometimes be down. And if you ever hit zero, the game is over. You can't come back from zero. The mathematics of this is called the gambler's ruin problem. And the answer is fascinating. With a starting bankroll of N dollars and a per round win probability of P, the probability of eventually going broke is 1 if P is less than or equal to 1/2. Certain doom. The only question is how long it takes. This is the tyranny of the negative expectation chain. Each round seems harmless, just a tiny edge against you. But round after round after round, those tiny edges compound. The chain of events drags you inexorably toward ruin. The casinos know this very well. That's why they're happy to let you sit at the table all night. They're not worried about any individual hand or any individual spin. They're playing the long game. And in the long game, the mathematics is on their side. Now, let me turn this around and ask a different question. What if the edge were in your favor? What if you won 51% of the time instead of 49%? Now the expected value per round is positive 2 cents. Over time, you expect to grow your bankroll. But here's the thing. You can still go broke. If you have a bad run early, before your bankroll has grown enough to absorb the fluctuations, you might hit zero and be done. This is why mathematicians talk about the Kelly criterion and bankroll management and all sorts of sophisticated strategies. Even with an edge, you need to survive long enough for the edge to matter. The short-term fluctuations can kill you before the long-term expectation saves you. This has implications far beyond gambling. Think about evolution. A species might have a slight advantage in survival and reproduction. But in the early stages, when the population is small, random fluctuations might wipe it out anyway. The mathematics is the same as the gambler's ruin. Natural selection can only do its work if the lineage survives the random noise long enough for the advantage to accumulate. This is actually a deep insight. Imagine a new mutation arises that gives an organism a 1% survival advantage. 1%! That's a real edge. Over millions of years, that should take over the population, right? Well, not necessarily. When the mutation first appears, there's only one individual carrying it. That individual might get eaten by a predator, struck by lightning, or simply fail to find a mate. The 1% advantage doesn't help if you die young by bad luck. The mathematics shows that even with a 1% advantage, there's about a 98% chance that the new mutation will be lost from the population simply due to random fluctuations. This means that evolutionary innovation is much harder than you might think. Beneficial mutations have to not only arise, but they have to survive the gauntlet of chance long enough to spread. Most beneficial mutations are lost. Only the ones that happen to get lucky in the early generations persist long enough for selection to amplify them. Think about technology startups. A company might have a slightly better product, a slight edge over its competitors. But if it runs out of money before that edge translates into sales, it dies. The chain of events, customer acquisition, revenue, growth, has to proceed favorably long enough for the company to reach self-sustaining scale. Here's a specific example I find striking. Suppose a startup has an 80% chance of surviving each quarter. That seems pretty good! 80%! But what's the probability of surviving 5 years, which is 20 quarters? 0.8 to the 20th power equals about 1%. 99% of companies with those odds don't make it 5 years. This is why venture capitalists invest in many companies, not just one. They're playing a portfolio game. Some investments will fail due to bad luck, others will succeed. The key is to have enough bets that the expected value works out favorably, even though any individual investment is quite risky. The mathematics of probability chains applies everywhere, and the key insight is always the same. The chain as a whole behaves differently from any individual link. You have to think about the whole sequence, not just one step at a time. Let me now try to explain this in the simplest way I can. Imagine you're explaining this to a bright 12-year-old. Here's what I would say. When things happen one after another, and the probability of each thing is less than 1, the chance of the whole sequence happening gets smaller and smaller. Even if each individual step is likely, the sequence might be very unlikely because you're multiplying fractions, 0.9 times 0.9 times 0.9, over and over, eventually gets very small. But it's worse when the steps affect each other. If what happens in step 1 changes what can happen in step 2, then you're not just multiplying fixed numbers. You're multiplying numbers that keep changing based on what happened before. And that can lead to surprising results. Sometimes the chain leads somewhere you never expected, just because of how the early links fell. This is why planning is hard. This is why prediction is hard. This is why that student's shoelaces could matter. Each event in the chain constrains the next event. A different shoe tying leads to a different arrival time, which leads to a different bus, which leads to a different set of possibilities entirely. Now, some people find this depressing. All this uncertainty, all these chains leading to unexpected places. How can we plan anything? But I find it exhilarating. Because here's the other side of it. If small changes can cascade into big effects, then small interventions can cascade into big improvements. You can't always predict exactly what will happen, but you can shift the probabilities. You can stack the deck in your favor. This is what engineers do when they add redundancy. This is what investors do when they diversify. This is what scientists do when they run many experiments. They're all doing the same thing, managing probability chains, trying to make the favorable outcomes more likely and the unfavorable outcomes less likely. And here's the deepest lesson. We live in a universe where probability is fundamental. Not just practical probability, where we don't know enough, but fundamental probability built into the laws of nature. Quantum mechanics tells us that at the deepest level, nature is probabilistic. There are chains of events where even God, if you want to speak that way, couldn't predict the exact outcome because the outcome isn't determined until it happens. Let me be more specific about this because it's so extraordinary. In classical physics, if you knew the exact position and velocity of every particle in the universe, you could, in principle, calculate the entire future. The universe would be deterministic. Laplace imagined a vast intellect that knew all these things and could see all of time laid out before it. But quantum mechanics shows that Laplace's demon is impossible, not just in practice, but in principle. A particle doesn't have an exact position and velocity. It has a probability distribution. When you measure it, you get a specific result, but that result is genuinely random. Not random because you don't know enough. Random at the fundamental level of reality. When a radioactive atom decays, there's no cause, no mechanism, no hidden variable that determines exactly when it happens. The atom just has a probability of decaying in any given moment. Over many atoms, you can predict statistics with exquisite precision. But for any individual atom, it's fundamentally unpredictable. This drove Einstein crazy. He spent years looking for a way around it. He proposed clever thought experiments trying to show that quantum mechanics must be incomplete, that there must be hidden variables we haven't found yet. But every experiment supports quantum mechanics. The randomness appears to be real. What does this mean for our probability chains? It means that the chains themselves are fundamental to reality. The universe isn't a clockwork mechanism executing a predetermined program. It's a branching tree of possibilities, with probability governing which branches are taken. At every moment, at every particle, dice are being rolled. And yet, somehow, from all this randomness, patterns emerge, regularities emerge. The laws of physics hold, not despite the randomness, but through it. Statistical laws govern the behavior of large collections of random events. producing the orderly world we see. Einstein didn't like this. He famously said, "God does not play dice." But as far as we can tell, Einstein was wrong about this. God does play dice. Or at least, nature behaves as if dice are being played at every moment, at every particle, throughout the universe. This is actually quite beautiful when you think about it. The universe has both regularity and freedom built into its foundations. The probabilities are fixed by the laws of physics, so we can calculate and predict averages. But the individual outcomes are free, genuinely open, not determined by anything. Every electron has a kind of creative latitude in choosing where to appear when measured. This means that the mathematics of probability chains isn't just a useful tool for gambling and weather prediction, it's the actual language of reality. The universe is a vast network of probability chains, each event constraining and influencing the events that follow, with the whole system evolving according to the rules of probabilistic combination. And yet, patterns emerge. Not deterministic patterns that let us predict exactly, but statistical patterns that let us predict on average. We can't say which radioactive atom will decay next, but we can say how many will decay in an hour. We can't say exactly where a pollen grain will end up, but we can say how far it will drift on average. We can't say what the weather will be in a month, but we can say what it's likely to be. This is the nature of probabilistic knowledge. It's not certain knowledge, but it's real knowledge. And for creatures like us, living in a universe of probability chains, it's the best knowledge available. Now, let me circle back to where we started, the student and his shoelaces. Did tying his shoes slowly really ruin his life? Here's what I told him. First, probably not, because ruined his life is too strong. Graduate school is a step in a chain, not the end of the chain. New opportunities arise. The path from here is also probabilistic, and many paths lead to good places. Second, even if it did matter, there's nothing special about the shoelaces. Every event in the chain mattered. If any of them had been different, the outcome might have been different. The shoelaces aren't more responsible than the traffic light that made the bus leave early or the professor who scheduled the quiz that morning. But third, and this is the important part, there is a sense in which he's right to be in awe. The interconnectedness of events, the way one thing leads to another, with each step constraining the next, is genuinely profound. We live in a web of probability chains, and our actions do send ripples forward through the web. This doesn't mean we should agonize over every decision. Most ripples fade. Most chains don't lead to dramatic consequences. But some do, and we can never know in advance which ones will matter. What we can do is play the odds, bias the chains in our favor. Take the small actions that, probabilistically, tend to lead to better outcomes. Show up on time. Do the work. Be kind to people. None of these guarantee anything, but they shift the probabilities. They load the dice. In a universe of probability chains, that's the best anyone can do. And it's enough. It's enough to build lives and civilizations and science and art, all of it built on the mathematics of chance, the multiplication of probabilities, the compounding of small effects into large ones. So next time you tie your shoes, think about it. Not with anxiety, but with wonder. You're participating in a probability chain. What you do now constrains what can happen next. Each step leads to new steps, new possibilities, new branches of the future. The mathematics is beautiful, and even though we can't see where the chain leads, we can appreciate the structure of the chain itself. That's physics. That's probability. That's life. And I find it absolutely fascinating. Now, I want to hear from you. I've told you about probability chains, how small things multiply into large effects, how events constrain each other, how we navigate a universe of structured chance. Here's my question for you to think about. What's the longest chain of events you can identify in your own life where each link depended on the one before it? Think about it. Write it down if you can. I'd love to know what chains you discover.